everybody. Thanks for tuning in today. This week, I'm super excited to introduce our seminar speaker, Dr. Stephen Sholes, who is currently a postdoc at NASA's Jet Propulsion Laboratory. Dr. Sholes is a planetary scientist and an astrobiologist whose research focuses on understanding the habitability of past and present Mars by looking at surface geology and also modeling its atmosphere. He received a bachelor's degree in astronomy from Cornell University and a dual PhD in Earth and Space Sciences and Astrobiology from the University of Washington, where we actually met as grad students a long time ago. After that, in 2020, he started his current position, or 2021, sorry, he started his current position at JPL working on the Mars 2020 Perseverance rover mission. And actually this week is LPSC, which is that big Lunar and Planetary Science Conference. And I know he's had several presentations this week for that. But today we'll be hearing about his work focused on answering this big question that we have about Mars, which is, whether Mars had oceans in the past. And he's going to be addressing this using mapping and quantitative techniques. And again, I'm really excited for this talk. And so thanks again, Dr. Sholes, for taking the time to talk with us.
Thanks thank you. So thanks for inviting me for this this talk. I'm excited to talk about this. So this is sort of a broad, overarching view of this research project I've had that's had many different facets to it, but trying to understand whether or not Mars ever did have oceans. Because as it always turns out, Mars, a warm, wet, ocean-filled Mars always captures the imagination of the media, of students and citizens and everybody. Because, you want to think about in terms of what is better for potential habitable environments, what's better for potential life to form. And when we think about that, having a giant body of liquid water on the surface is a very good habitable environment. So that's really what we want to think about. But it turns out one of the big problems in Mars science is trying to understand whether or not past Mars was warm and wet with oceans and lakes and liquid body of water, or was it cold and dry in which you don't have that much total water available at all, and you only have ephemeral periods where liquid water can flow on the surface. Because we do know that that water did flow on the surface of the planet sometime early on in its history, but we don't know how long lasting that was. And we definitely don't know if there are oceans. And hopefully I'll be able to convince you that by the end of this talk. So one of the big questions is, why do we even think that there were oceans in the past? So as I've said before, we have evidence from valley networks. We have evidence from the rovers, from crater lakes and deltas that we see on the surface with orbital imagery and with the rovers. So we know that liquid water is flowing on the surface. But oceans are these, when we talk about oceans, we're talking about almost like an entire hemispheric ocean on the northern part of Mars. So here's a topographic map of Mars. Blue are the lows, reds and whites are the highs. And you can see that there's this, what we call a topographic dichotomy on Mars, in which the northern part is much, much lower than the southern highlands. And more specifically, the northern lowlands here are actually smoother, younger, and flatter than the southern highlands. And what really kind of drew this hypothesis that Mars had oceans in the beginning was you have all these large outflow channels, primarily here in the Circum-Chryse-Planitia region. And it's largely believed that these outflow channels were carved by water. And so these are very big features and will require vast amounts of water, and where is that water going to go? And so it seems pretty obviously if they're flowing out this way, down slope, they're going to end up in the northern lowlands, which could act as a giant basin for all this water to pool. So if you're able to have a lot of water flow out into the northern lowlands and pool there and be able to sustain there for a long amount of time, then we would have an ocean. Of course, if this was filled with an ocean, that would suggest that there are potential shorelines, which I'll get to in a little bit. Um, but there are problems with this idea that Mars had oceans. The first one is that we have yet to find significant geochemical evidence that there were oceans. So if there was a large ocean covering almost the entire northern hemisphere of Mars, we would expect to see the geochemical, the mineralogy to reflect that. And we're not seeing things like evaporites and large carbonate deposits, things like that. In the northern lowlands. It doesn't mean that they're not there. They could be buried or altered or destroyed, etc. But we're not seeing anything there. You could think, oh, well, let's just, we don't have any drills on Mars, at least deep enough to answer these questions. But we have radar on our orbiters to basically try to probe the subsurface of these northern lowlands. But the results from these radars are ambiguous. They could be either very vesicular basalts, or they could be like marine sediments. And so it's still up in the air whether or not that is supportive of an ocean or not. Do we actually have enough water in the past to fill up an ocean up to this sort of level? And so there have been investigations looking at the deuterium to hydrogen ratios to assess what the past water inventory was on Mars. And they are also ambiguous. And in some cases, you actually do have enough water early on to fill up an ocean's worth on Mars. And in some cases, in some estimates, you actually don't. I think this slide probably could be updated a little bit, but it seems now, from what at least I've heard in LPSC this week, actually, is that past water inventories probably were enough for an ocean, but still, they're still ambiguous, it's still unknown. Another big problem is that the proposed shorelines, which most of this talk is going to be investigating, have vast ranges in elevation. So you expect to have an equipotential surface, just like on Earth, you have a sea level due to gravity. On Mars, you would expect that you have a fairly flat surface wherever that water was pooled, and instead we're getting almost 7 kilometers difference in range along this dichotomy. So that poses a problem of why is that? So I keep talking about proposed shorelines, so we'll get a little into the nitty-gritty of what I mean by that. And so there are two primary proposed shorelines that have persisted since the late 1980s. One is the Judernihilus level, and I'm using the term level not to mean it's topographically level, but just as a sort of non-genetic term to describe these, because we don't know if they're shorelines, so we don't want to address them as shorelines. We don't want to address them as geological contacts, because in some cases they aren't geological contacts. And so the literature is kind of settled on level, which still is not great in my opinion, but it's what we have to work with. So we have the Judernihilus level, which is a possible younger, smaller proposed ocean stand. This one actually has been mapped pretty well globally, and you can see here in the white dots here on this topographic map where this lies. So it's kind of scattered about, but it's much more closer to the pole because it represents a smaller stand. The Arabia level here in the black lines is a possible older, larger proposed ocean stand, which would be a much larger ocean with much, much more water. And there are other proposed possible putative shorelines, but we're not going to address those because those have not been mapped to any degree of success. And there's much, much, much less evidence for those. But it's important to note that those have been suggested. So there are a couple geomorphological observations that have been used for supporting this. One is these proposed shorelines, and so I'm going to be talking a lot about those here on the left. This is just a stereographic polar projection map. There are suggestions that there might be wave-cut cliffs because actually most of the shorelines on Earth are also cliffs. But these occur in very small segments, and they're also in an interesting spot that might be disconnected from the rest of the ocean. But anyway, those have been suggested as evidence for oceans. You have these polygonal terrain found throughout the northern plains here, which could be the result of desiccation of marine sediments. And so these also have been suggested as evidence that there was a large body of water here. We have these so-called open basin deltas. So these proposed deltas that flow and are open up to the northern plains themselves. So those have also been suggested as evidence that the northern plains were filled by a large body of liquid water. And then there's putative tsunami deposits that have been suggested that, oh, you might have had an ocean body of water, a giant impacts crashed into the ocean and were able to create giant tsunamis, leaving evidence. But again, I'm not totally convinced on that evidence either. But the big thing is that, and this is one of my favorite quotes I love throwing around, is that a lot of people just assume, oh yeah, Mars had oceans in its past. But this quote from Maria Zuber in 2018 is that the most compelling evidence that Mars once had oceans is the presence of potential shorelines. So it kind of shows you that, you know, all this other evidence that I've been showing you, I've kind of shown you, it's like it's ambiguous, it's unknown, and the biggest evidence for these proposed oceans is this idea that these two features from this 1989 map that I'm showing here are indeed ocean shorelines. But there are still problems with that as well, being that, one, there's no detailed investigation of these shorelines that has been completed yet. We now have near global coverage of high resolution data at around 6 meters a pixel using the context camera on the Mars Reconnaissance Orbiter. And no one has really used this data to go and show that, yes, indeed, these are geomorphologically marine shorelines. There's another problem, and I'll get to this later on in the talk, but there's problems with the sharing of data, and this is an important thing I've been really pushing for in terms of just geosciences and science in general, is to share the data and be open with it, because there is no mapped putative paleoshorelines, no geospatial data that's publicly available so people can test and replicate this and do their own investigations. And this has actually caused a lot of problems down the line, specifically for these proposed Martian shorelines. The locations of these are very unknown, and that stems from the fact that people map these and they have their own ideas of where it is, but they either can't show it because they no longer have the geospatial data from decades and decades ago, or it's just not available. They've lost it. I've contacted a couple people about trying to get some of these data, and they seem to be gone. So coming up with a way to archive this data is an important thing, and so I keep using some AGU journals, and I applaud their data repository policies. And then again, as I told you, the climate models have a hard time keeping liquid water on the surface, and so a lot of these models predict that the water would pool for a little bit, but then very quickly migrate into water into the ice sheets, and so you wouldn't be able to have a sustained liquid water ocean. So the goals of this broader project that I've been working on are manyfold. So first we wanted to understand how can we even test these as paleoshorelines? Because they keep saying, we want to test these as paleoshorelines. So we have to come up with a methodology that is applicable to Mars, Earth, even Titan, places where we would have potential shorelines, and be broad enough to be able to characterize it and come up with a way. So that way, I was just talking this week at LPSC, and oftentimes with these sort of photogeologic studies, it's the classic, is it a rabbit or a duck picture? People can look at things very differently and come up with very different conclusions, which is a great thing of having a diversity of people. But we also want to make sure that when we're looking at things and claiming that there are oceans on Mars, that we have a good way of just testing that quantitatively rather than just purely qualitatively. Although you do need qualitative analysis. It's I'm not trying to throw that out. Um, we want to evaluate what these proposed geomorphic features are. So once we figure out how we can test it, we want to apply it and actually see what do these features actually look like. We also want to understand where these features are. Um, because I told you they don't follow an equipotential surface, we want to understand why that is, if they are shorelines, a big if there. But then we also want to understand whether or not we would even expect shorelines to form and whether or not we would expect them to be preserved. So those are two other questions. And so I put a couple of citations here, and I'm kind of just banging these out one by one, including with Dr. Rivera Hernandez on a recent paper that just came out last month. So for those unaware of what I mean by shoreline, let's do a little bit of shoreline 101 here in terms of what do I mean when I talk about this. So there are two main types of shorelines. One are depositional shorelines. So these are where you have a large amount of sediments being applied and it's being deposited, and so you get things like beaches. So beaches themselves, where you get sandy beaches, that is a depositional shoreline. But then there's also lots of other ones. You get these things like barrier islands. I don't know if you can see my mouse, but here on the left, you get barrier islands. You get these things called tombolos, which can connect up to little islands and such. And you get these little spits and these longshore ridges you can get as well. So basically, you're just having a large amount of sediment that's being deposited along shore. Pretty simple. Things that we typically think about when we think about beaches. But more commonly, it seems, there are erosional shorelines. So these are caused by abrasive wave action, primarily, which forms a large terrace. So a large flat to very slightly dipping feature. And then it's mostly caused by the abrasion action of waves, but then there's also hydrodynamic processes caused by the water interacting with the rocks. And basically you form wave-cut cliffs, you form wave-cut platforms, and so that's what we're trying to test for when we think about depositional features. So one of the questions I mentioned before is, first of all, do we even expect these types of shorelines to form? Do we expect depositional landforms or erosional landforms to form on Mars? And so a couple studies have actually taken a look at this, namely Banfield et al. 2015 and Krall et al. 2006, where they basically investigated how much wave energy is required to erode out a narrow bedrock terrace. And it turns out that, I'm not going to go through this entire plot, but just think of it this way. This is representing wave energy. And so most of these blues and greens is where the wave energy is insufficient to carve out an erosional terrace. Whereas the reds and the yellows is you actually do have the ability. And when I say that, I'm talking about this is modeling all the different unknowns of what goes into wave energy. So you have to think about the wind speed, you have to think about atmospheric pressure, and you have to think about fetch as the sort of three main proponents for that, or components of that. Fetch being basically the distance you have for the wind to blow up and create these waves. So it depends on the geometry, the topographic geometry. So all in all, it just means that there's a wide unknown parameter space for past Mars because we have lots of unknowns in terms of its climate. And most of that parameter space is insufficient to carve out shorelines. But it's not an impossibility. There are lots of parameter space where you can do it, but the majority, you can't do it. And then the other flip side is you have things like impact gardening. So you have lots of impacts that are basically going to churn up the soil over 4 billion years, 3 to 4 billion years. And this churning the soil can actually completely degrade very thin features. So if we're talking a terrace that is maybe 10 meters wide, the constant amount of impacts that are hitting Mars's surface over that time can actually erase these sort of small features. So it's important to understand, do we even expect them to survive? Possibly not. You've got 3 to 4 billion years of erosion, wind erosion, possible hydrologic erosion, and impact erosion. And in fact, this week, a collaborator and I have been working on a project where we look at just direct impacts themselves. So not even like impact gardening with smaller craters and impactors, but things that are about 100 meters, forming craters that are at least 100 meters. And it turns out if you actually just take a sampling of 4 billion years of cratering, and look at how those things would actually intersect with these proposed shorelines, it turns out that older features, so like the Arabia level is proposed to be about 4 billion years old, 70% of that feature would be directly obliterated or buried by an ejecta blanket of these craters. So we don't expect to see global features at all just because of the age of these and the constant bombardment by impactors. And in fact, if you look at looking at the segmentation of this, it turns out that the intersection of all these craters will create segments that are basically all less than 35 kilometers. So we don't expect to see large swaths of these proposed terraces that have been constantly being mapped in the literature. So all in all, it's just that large continuous segments are unlikely for these older features. We can drink. So that goes into, okay, can we preserve these? Can they form? So how do we even detect these? So I've developed sort of this quantitative toolkit for identifying paleoshorelines. So this is from my Sholes et al. 2019 paper. And there's a variety of different facets because you can come at this in different ways, and each one can help provide a piece. And it's sort of, if you're claiming oceans, you ideally would like to have more than a single line of evidence. You want to be able to have multiple lines of evidence to make such a broad, large claim. So the first thing is the same thing that's been going on, is doing geological mapping and classification. So we kind of went through and thought about, okay, what are the different features that a shoreline might form, like those spits, those beaches, tombolos, wave-cut cliffs, etc. And what are things that can be geomorphologically similar using orbital data? And so we come up with sort of a 5 classification scheme where you get things like volcanic lava flows that can create features that seem very similar. Glacial features can also form features like eskers that can be interpreted as coastal ridges. Coastal features themselves, so we went through and looked at a lot of the terrestrial literature of classic and sometimes more exotic features. Impacts themselves, and then other, which is kind of just a catch-all term for things like albedo contacts, where you're seeing maybe just a change in the geological lithology, mass wasting along steep slopes, faulting. You don't have too much in terms of tectonics on Mars, but you do have faults, and those can form similar features. So the first thing is to map out these features. So here's an example where we've mapped out these curvilinear features that have been proposed as paleoshorelines, and then kind of investigating, okay, this turns out to be one of the better cases that fit into what we'd expect for coastal morphologies. But they also fit into other things like mass wasting, and I'll get to that in a second. There's spectroscopy, so looking at the mineralogy from orbit. It's a little bit harder to do this with all the dust on Mars. and fortunately, our one of our primary spectrometers in orbit has failed a few years ago, so we're not getting as much new data there. We can look at thermal inertia and the thermophysical properties. So thermal inertia is essentially how well a material is able to retain heat as a way. So you can look at this as sort of a way to attest what are we looking at in terms of like bedrock or how lithified or indurated a feature is, grain size. There's all sorts of effects that go into it. But one way you can think about it is if it is, like grain size, you can look and see if you see sorting along this contact, like you would expect at a beach, etc. We can use crater counting to get relative and absolute ages, especially when you're trying to build up like a stratigraphic sequence of what has happened. And then my big contribution here has been doing topographic analyses to understand, to form a quantitative way to test for specifically erosional marine terraces. So what I've done is taken a simple model that's been applied to Earth paleoshorelines, and for the first time, adjusting it and now applying it to possible Mars shorelines. And so the way this works is just a quantitative method that looks at the topography and is able to actually parse out subtle variations in those topography of where a shoreline might be. So here where it's labeled Earth, this is a LiDAR image of the Lake Bonneville paleoshorelines in Utah. So the Great Salt Lake at one point was much larger, called Lake Bonneville, and it formed very striking paleoshorelines. So you can see where it's labeled B and P, that's the Bonneville and Provo paleoshorelines, and they are very easy to pop out. You can see very clearly that we're getting tens of meters wide terraces. And then where you can see in the middle between the P and P, there's an I. And you can definitely see that there are these curvilinear features that look to be indicative of different lake levels. So I for intermediate, these are intermediate lake levels. But they're very hard to actually pick out exactly where they are. And in fact, I believe I was reading that Gilbert himself would stand here and would have a hard time picking out exactly how these intermediate features presented themselves. So the way that this, what I unimaginably have been referring to as topographic expression analysis, works is you take the topography. This is an example of an idealized terrace in red here. You take this topography of a possible terrace, you fit to it a idealized slope. So you kind of basically look at a trend surface to see what would this feature look like if there was no possible terraces there? So kind of just almost like an average, because it's a trend fit to the surface, this orange dotted line. If you subtract the two, you get the residual topography. So that's what here in B is. And if you take the first and second derivatives of that, if you have a terrace, you're going to be seeing these very specific features in the derivatives that represent different points along this terrace. So the first one you would expect is this riser inflection, where you're having the steepest slopes as it's coming up to the terrace. This only happens when you have multiple terraces that are stacked on top of each other, but you're seeing it as a maximum in the first derivative. And then you get the riser crests, where you're having this change in curvature at the very peak, or at the very beginning start of the terrace, which you find as a minimum in the second derivative. The bench top is the flattest part of the terrace itself, which is a minimum in the first derivative. And then you get the nick point, where again we're having the change in curvature, which is a maximum in the second derivative. So we can find these four features in order. We can quantitatively say that yes, this is a good candidate for paleoshorelines. Like, it's doing what we would expect for a terrace. But again, we want multiple lines of evidence. We don't want to just rely solely on this, because there are other ways to form terraces other than through marine processes. So we can apply this both in 2D in the maps and then also along topographic profiles themselves. So here's an example where we have the high resolution imagery here in A, where you can see these curvilinear features that follow the topography. If you look at the actual topography, we get some high resolution. This is about a meter a pixel. We fit a trend surface to that, and then we can subtract it to get this residual. And you will clearly see in the residual topography these alternating dark and light bands. And so this is an easy way that you can, in GIS applications, quickly be able to assess whether or not we have any candidate paleoshorelines, because we can quickly see that you are having these alternating bands in the residual topography, and then therefore that's a place you would want to go and follow up with actual topographic profiles and more analysis. So we built a tool that can be, quickly automated and applied to assess large swaths of topography on Mars. And when you zoom in, so here is a zoomed in part of A. We've done a bunch of topographic profiles here, and then we apply the same sort of topographic expression analysis along each individual feature. And I've actually hand checked these all by hand, so I didn't rely just on the automation because I wanted to check to say, oh yeah, that looks like it possibly could be a terrace, or if it was giving me an example, I wanted to double check to make sure that it was pulling out the terraces, because you want to avoid false positives and false negatives. But we found a bunch of different terraces, but they don't have any topographic or spatial cohesion that would suggest that these are indeed a paleoshoreline surface. And so if you look at the slope map itself as well, you can see that, yes, a lot of these do fall in places where you have flat slopes that are kind of bounded by steeper slopes, which is what we'd expect. But they don't follow the same feature. And when you plot the elevation, you kind of have something here at like the negative 3.8 kilometers, where you're getting a grouping, these higher ones here in the south. But even then, you follow them, they laterally do not trace out either in the visible imagery or in the slope, the topographic slope data, any sort of continuous feature. So the question, of course, is what if they're not shorelines because they're not seeming to behave the way that we expect them to, then what are they? And there are a couple different ways for these particular examples, because again, this was sort of the one of the most prominent places that might be a shoreline on Mars, where the resemblance was very striking. And our hypotheses here is that what we're actually seeing is either differential erosion, where we're having changes in the resistance to weathering, and therefore, as they erode away, we're kind of seeing the flat parts of the different units forming these sort of nick points, and that's kind of forming these terrace-like features. The other one is that you're having mass wasting along the steep slopes of this crater rim, because this features along a crater rim, and it's basically falling down, creating these sort of terrace-like features. And that would explain why it's not continuous along the rest of it, because what we're seeing is multiple different features as they're falling down. So both ways are able to explain that and don't require that these are a shoreline. And we've done more investigations. I go see the whole paper for a full breakdown, but there's a lot more in terms of the topography and analysis of the individual sections themselves to show that this does not behave anything like we would expect for a shoreline, which is a little unfortunate, but that's just the way the data has fallen. So what we did is I did a survey of the literature to identify globally all the different features that have been proposed as possible shorelines on Mars. We found about 40 different features, about a little over half of which had high resolution data available. And here's a map of just where they're all located. You can definitely see that some places have a lot more investigations than others with these little diamonds. But what we find is that they break down into three primary morphologies that can be identified. So they're either terraces, so like I've been explaining, ridges being proposed as a depositional coastal ridge, or these lobate flow fronts, which have been suggested as marine sediments being deposited. And this is what they are. So when people say that there are shorelines on Mars, these are the types of features that they're referring to. These are the 40 different features. I love showing this because people don't often realize what it is people are talking about when they say we think we found shorelines on Mars. And this is what they're looking at. Um, and one of the striking things when I look at this is there's nothing really here that pops out as that looks like a shoreline. In fact, there's lots of places here that have wildly different interpretations from other research groups. I don't know if you can see my mouse, but on the far left, third down, you get these things that have been suggested might be coastal ridges. But another research group has suggested that this is actually the caldera of a supervolcano, and these are just ridges that are forming from cracking during volcanic episodes. Um, so these are the different places. Some of them are more interesting than others. Some are possible coastal morphologies, but most of them are going to be suggested depositional features. Hang on a second. So out of all those features, these are sort of classic representations. Actually, these are type locations actually for the different Judernihilus and Arabia level. So the Judernihilus level, as I said before, has been mapped because it is an actual contact that you can actually map. So you get these lobate flow fronts, but what's interesting is actually they actually flow upslope. So this is actually moving upslope here, and then you get these sort of curvilinear features that follow a long track with the lobate flow fronts. The Arabia level, on the other hand, has a wide array of different morphologies, but most classically, it seems, while you can't see it in the visible imagery, when you look at the infrared mosaics, it's striking that we're seeing it as basically this little black and white contrast between possible different geological or units. So as I was saying before, we kind of took an example and look at the Arabia level and tested whether or not it was using all the different schemes that I had proposed in my toolkit. When you look at it, but it lacks landform cohesion. We see actually bifurcation, which is not what we expect of terraces. So here's an example here where in high resolution, this lighter feature, I don't know if you can see my mouse, but this lighter feature here in the top right follows, but actually bifurcates, or these white arrows are. Again, we're also seeing bifurcation in D, what the little white arrow is. And they don't form an equipotential surface. So when you look at individual terraces along cross sections, it's very striking that they do not follow what we expect how they behave. So unfortunately, this prime example is unlikely to be a paleoshoreline. And when we apply this to those 40 hole sites using the same sort of methodology, these are sort of the original interpretations, is that we're having strand lines, which are kind of like lake levels or bathtub ring sort of features, wave cut platforms like I was discussing, tombolos and spits, coastal ridges, just ocean sediments, stacked terraces. But when we actually look at what the new interpretations are, what we're seeing oftentimes is that we're just getting this sort of like slumping or mass wasting along crater walls or steep slopes. We're getting erosion-resistant weathering, like I was showing you before. Eskers, so like this feature has been proposed as a coastal ridge, but actually flows uphill on the top of these mounds and going over topography, which is not what we would expect, but is possible with eskers. Again, some more sort of eskers that can form in troughs, debris flows, more crater wall slumping. So out of all the 40 different candidates, we only had one that was uncertain, and we couldn't totally just rule out as this doesn't fit into any of these new sort of candidacies. But even then, it's in a place that is unlikely to be an actual ocean shoreline and would more likely be a large sea. And again, we are seeing some weird things like bifurcation in these features. So even then, it seems unlikely that any of these could be shorelines. The one exception, though, and there's a bit asterisk here, is the Dune-Nihilist level in its entirety. And this is because this is not an erosional shoreline, but it is some sort of depositional feature. And liquid water was probably involved in its placement, but we don't know to what extent. So we can't rule out that this is essentially ocean sediments forming a quote-unquote shoreline. But there are lots of pet theories that have been thrown around by various different groups, ranging from groundwater activity to CO2 charged fluid of sediments, tsunamis, mud extrusion with like mud volcanism, debris flows, or possibly debris flows into an ocean as well. So there's a whole wide range. And so it's very uncertain what this is. And so more investigations need to be done. I don't want to spend up too much time, so I'll quickly go through some of this other stuff. But essentially, the history of these features themselves is careful with my wording here, but is very odd. No, I shouldn't say odd. The history of these map shorelines is tumultuous, being that originally these were hand mapped on printout of Viking mosaics at around 200 meters per pixel. They were updated with a little bit of new imagery in the late 90s. That was created into a figure, a low resolution figure, which was then digitized by another group, which also required smoothing and interpolation of those linear features. That data was then provided to other research groups that threw out about 2/3 of the features to only take the largest continuous segment. That largest continuous segment of the smooth interpolated digitized version of the low resolution hand-drawn maps has been shared to all the other groups because that's the only file that's still sort of existing out in the open. And then these large papers that have been trying to assess why does that feature, that last feature that's been proposed, not form an equipotential surface. And so there are varied degrees of error that keep getting introduced along each of these different points here, which causes problems. And this is one of my favorite figures that I've made because it shows how this data error propagation has fallen. This white line here on the left is the Arabia level as originally proposed. So I remapped it using the original geomorphological definition in the late 1980s. But the file that keeps getting shared is this yellow line in the south. And you can see, A, the resolution of that is pretty bad. B, it's not following the feature at all. In fact, it's about 500 kilometers south. And C, it's cross-cutting weird topographic features. So it's actually, you see it's cross-cutting these craters, these channels. And so this is causing huge amounts of problems in terms of where the elevation is. So the mean elevation of my segment here is a whole kilometer lower than the mean elevation here. And this one has huge amounts of standard deviations to the south as well. And so what I did was I actually took all the different mappings of the Arabia level has been proposed throughout the literature, plotted them all together, and then came up with a method to determine what the minimum offset, lateral offset between them all is. And the average across the entire planet is about 150 kilometers, getting all the way up to over 1,000 kilometers in some places. So you can see that because there's no good standardized geospatial data, we actually have no idea really where this feature is, which can cause problems because they don't form an equipotential surface. And here in the bottom plot here, the Arabia level, you're seeing this huge variety. You're seeing about 7 kilometers of elevation range between the different mounts of plots. So each of the different colors is one of those different mappings. They all seem to follow the same sort of larger trend. And so a couple studies have tried to propose, well, if they're all following this sort of similar trend. Maybe there's some sort of planetary deformation that's going on that's causing this to happen. So one of those examples is this true polar wander model, in which the Tharsis volcanic province, one of these where Olympus Mons is located, as it grows, it causes the planet to reorient itself to get that large mass at the equator, and so it just shifts the entire planet so that it can form better equilibrium. Um, so if Tharsis formed near the poles, this can explain these large trends according to these studies. But it's more likely that Tharsis formed based on gravitational data that it formed near the equator, and there was only a little bit of this true polar wander that was being caused. And so when this moves, you form a new equatorial bulge, and mass is redistributed from the paleoequatorial bulge, and that's what causes the surface deformation. So this is what they had originally, Perron et al. 2007 had originally proposed, is that you can see their model results of this seem to fit the long wavelength trend of that one segment. But there are lots of problems because A, they didn't include these other segments that I denote here with these blue lines. So you're missing large swaths. It requires some unknown and unobserved internal loading device to actually form this because of Tharsis formed near the equator. And it actually just optimizes the model to the shoreline data itself. So if you put garbage into your model, because we don't know where these shorelines are, as I showed with the mapping, you're going to get garbage out. So other proposed features include the Tharsis-Induced deformation model, in which the rise of the Tharsis volcanic province itself would have actually deformed the surface. This is nice because this is based on gravitational data and happens whether or not there was a shoreline there or not. So it's something that we need to take into consideration just for paleo features in itself. So if you're doing something that happened before or during the rise of Tharsis, you need to take in consideration that the paleotopography would have been different. But again, this data itself was missing large swaths and also requires additional loading modeling. So what I actually did is I actually replicated this Tharsis-induced deformation model with a little bit of the true polar wander and applied it to the features. And while they claim that their model in this black line follows the long wavelength trend of the data, when you actually plot the actual paleotopography, which are these red dots, you still see that you're having about 4 kilometers, 3 or 4 kilometers of elevation range. So the paleotopography still does not represent an equipotential surface, which is important. So actually, you apply this to all the different mappings and to characterize what the paleotopography would be. And this is a nice little plot of that, where it's showing each color represents a different mapping of it. And the left bar, the M, is the modern topography, and then the P is the optimized paleotopography. And you can see that even when you're applying, optimizing for what the paleotopography is based on its relative formation to the Tharsis volcanic province, the paleotopography still does not represent an equipotential surface in any way, shape, or form. You're still getting many, many kilometers of elevation range and large standard deviations. These ones here on the far right, the Webb-Parker 2010 and the My 2021, are very small regional mappings. So that's why you're not having as large of a range in them. And just to sort of conclude, as I'm running out of time and I want to allow some questions, what I'm doing now in my postdoc work is trying to understand what the lake levels are at Jezero and actually taking the same paleoshoreline toolkit that I've developed for testing for ocean shorelines and now applying it at Jezero, which we know was a lake, to test whether or not we actually have shorelines there. Because we know that there was liquid water here, unlike an ocean on Mars. The rover has shown that, orbital data has shown that. But that way we can understand the different changing lake levels. So if we can identify potential shorelines, we can understand how has Jezero as a lake evolved in the past, and therefore, how did these potential habitable environments change over time, and what were the different lake volumes, et cetera, over time. Um, and so we've got great new observations, just kind of plugged for the Perseverance rover. We've observed these deltaic cliniforms, observing at this Kodiak delta remnant, which is just very amazing. And that this actually provides the lowest constraint on lake levels that we've ever had now that we've observed this. So on the right here is an example of what that lake level would be in terms of where the past, essentially one of the only lake level constraints is this black line here, which is related to the delta and the outflow channel in the northeast. And so we're getting some great new data from the rover to help constrain the different lake levels. But when you apply the Paleoshoreline Toolkit, we unfortunately aren't actually seeing any of these candidate shoreline features. This may be just because we haven't got good enough data to analyze. I also haven't been able to analyze the entire crater surface due to lack of available high resolution data. But again, it also kind of falls into one of my original slides here is that do we even expect to have shorelines form? And the question is, we might not. So it's not totally unprecedented that we're not observing potential shoreline terraces here in Jezero. And so just some concluding remarks that I hope you can take away is that the evidence for oceans relies primarily on the fact that these proposed features are shorelines. But as I hopefully have shown you all, is that the Arabia level, this proposed older erosional ocean stand, is unlikely to be a shoreline. It's poorly mapped, it's poorly unknown what it is in the literature, and therefore it's unlikely to be a shoreline based on the data. The Junanis level, on the other hand, we can't exclude it as being a coastal depositional shoreline, but there are a wide array of other features that don't require subaqueous deposition to form it. So it's sort of up in the air, and hopefully, research can help tease out, because it would be great if it was marine sediments, but again, we don't know. We don't want to just go and automatically assume that it was. We want to take caution when using the map shorelines, and as just a general scientific figure is, if you're doing modeling work, make sure you actually understand what you're actually using, what the data has come from, because it turns out that this sort of data that people keep using in their models for these potential shorelines has such a hardened history that no wonder, some of their results may have been off. They do some great modeling work, but if you relies heavily on that data. So understanding where that data come from, problems with that data is very important. We have no obvious or unambiguous evidence for paleoshorelines, full stop, unfortunately. And Occam's razor says that most of these sites that can be explained through non-oceanic processes. So if you're going to make a big claim of oceans, that's require a good amount of evidence to back up that claim. And while these geophysical deformation models can explain some of the topographic trends, when you actually look at the actual paleotopography, you still have elevation ranges that can be considered that they're not an equipotential surface. So thank you, and I will be happy to take questions.